Okay, folks, good evening. I'm here to do another horizontal projectile problem for you. This is the first time I'm using this software, and my pen is not all that precise in the way it writes, but I'm going to do my best here. So here's the situation. You can see the diagram here on the screen. We've got a burglar that's trying to evade the police by running across some flat rooftops here. These buildings here that are in orange are the roofs of the buildings. And he's running with a speed of 4.5 meters per second, and then has to decide whether or not he should jump down to the next building, which is a distance of 6.2 meters away horizontally, but 4.2 meters below. Now, the solution to this problem can be done a number of ways. I'm just going to show you one possible way. Now, the way that I'm going to look at this is I know that the time spent moving in the horizontal direction is also the same time that he will spend moving down. So what I'll do is actually solve for the time that he's going to take to fall down a distance of 4.2 meters as gravity pulls him down. And once I know that time, I'll then determine, can he move that whole 6.2 meters in that same time. So let's start off by just listing what we know in the problem, separating our x and y variables here. That helps to keep our x and y motions a little independent. Since he is only moving horizontally, this initial velocity in the x direction, I'm going to list here in the x column, meters per second, 4.5 meters per second here. And I'm going to assume that he jumps horizontally, so straight off this building. So in other words, he doesn't launch himself, kind of up at an angle off this building. So in that case, his initial y velocity, so v0y here, is equal to 0 meters per second because he's going to project himself straight off this building. We know that any projectile moves in the x direction with no acceleration because there's no force there to make it speed up or slow down. So that's a 0 meters per second squared there. And the acceleration in the vertical direction is the acceleration caused by gravity, which would be negative 10 meters per second squared there. Okay, let me just clean up that little unit here. Okay, meters per second squared. That's not much better. But anyway, so as I said, I'm going to approach this problem by first just looking at really how far does he travel in the y direction. We know that he's going to move negative 4.2 meters down if he were to land on that next building. And from that, I can find out how much time he spends traveling. And then from there, use that over here, that same time, to solve really how far will he move in the x direction, okay, and compare that to the 6.2 meters. So looking at the y column here, I'm only missing time. So really the best equation would be my displacement as a function of time. So I'm going to use y equals y0 plus v0 in the y direction times t plus 1/2 times the acceleration in the y direction times t squared. Now, my initial y displacement, or position rather, I'll call it 0. We'll set my origin equal to, the position at the top of this first building, so right up here. And the initial y velocity, as I said, is 0 because he's just going to run off this building horizontally. So from there, I can really substitute in, he's going to move negative 4.2 meters in the y direction, set that equal to, this is an equal sign here, 1/2 times negative 10 meters per second squared times t squared. And so really it's a negative 4.2 meters here is equal to a negative 5 meters per second squared if I just multiply that 1/2 by the negative 10. And then I still have that term t squared there. So dividing both sides by negative 5 meters per second squared, negative 5 meters per second squared. You'll notice that the units here, let me use a different color, units here of meters are going to cancel. The second squared it will flip up to the top, which when I square root to get the t squared, that will just become time in seconds. So let's do this math here. 4.2 divided by 5 on my calculator is 0.84, and when I square root that, 0.84 is 9 point, so let's see, the time here is then equal to 9 point, or rather 0.9165. So let's call that 0.92 seconds. Okay. Okay, so that's seconds there. So based on that, I can now just look at how far is he going to move in the x direction. So in the x direction, our position really as a function of time is just strictly dependent upon that velocity in the x direction times the length of time that he's moving. In class we used v0x here, is ultimately how it boiled down because there's no acceleration in the x direction. But recognize that this value here, that x velocity, is constant. So it's really just, when there's no acceleration, it is that horizontal velocity. And you might already recognize that if he's moving at 4.5 meters per second and he's traveling for less than a second, 0.92 seconds here, he's not going to actually make it that 6.2 meters. But let's do the math here just in case. So 4.5 times 0.92, and that gives us a horizontal displacement then of 4.14 meters, which is too short. So yes, he will not make this jump at his current speed. Okay, no good. So now what I'd like to do is actually to see, kind of change up this problem just to go a little bit further. What speed would he need to actually make this jump? So let's take a look, and I'm just going to erase all this stuff here and now make this kind of into a new problem. So instead I'm going to cross out this Vx here and say, if erase this x displacement as well as a question mark. Let's actually use that x displacement. So in the x column, I'm going to add this 6.2 meters, and I'm going to say, what is the velocity that he needs in the x direction in order to make this jump? Now we already know the time that it takes him to travel down the 4.2 meters. So we can still use that time. That's kind of independent of this horizontal velocity. The motion, that's the whole idea here, this independence of vertical and horizontal motion. So I'm going to fill in that time of what we calculated it to be before, 0.92 seconds. And using that, since I know time is also in the x direction, I can put that over here. Okay. And now I can just use this simple relationship here based on how far he needs to go in the x direction. In that 0.92 seconds, I can solve for that velocity that he would need. So in the x direction, I know that he needs to travel 6.2 meters, so 6.2 meters in 0.92 seconds. So let's do that math here. 6.2 divided by 0.92, and that would work out to be 6.73 meters per second. So this is the minimum speed that he must have in order to make that jump. Anything beyond that, then he will, he'll still spend 0.92 seconds falling down this distance of 4.2 meters here, this displacement here, independent of how fast he's moving horizontally. But anything beyond the 6.73 meters per second is going to allow him to kind of, do this in a different color, project himself out further during that 0.92 seconds that he falls. So let's actually expand this and make it a third problem now. Let's assume that he is in fact moving at that 6.73 meters per second and makes this jump. And my question is now, what is his impact velocity or his impact speed when he strikes the ground? So let's fill in a couple of things here. So we just said that this initial, actually I'm going to change my chart here. His x velocity here is now, we said, 6.72 meters per second. I know that doesn't really quite look like a meter, but that's just the pen that I'm working with here. So anyway, I want to know what is his impact velocity. Okay, so let's sketch this out here. Let me erase this here. Impact velocity. So, as I said, he's going to project himself out. So let's go back up to our sketch here. He's going to project himself out at this initial speed of 6.72 meters per second. Now, as he moves through the air, he will maintain that horizontal velocity. So at any given time, he's still moving in the x direction. But his vertical velocity, let's draw that in yellow, increases with time. Okay, the initial y velocity here is 0 to start. So I can barely squeeze that in with my pen. This initial velocity of 6.72 is in fact just his x velocity, right? So I'll just write that as Vx. Oops, hang on. All right, well, at any rate. So what I want to do, let me actually just clear this screen. Let's draw a better picture here. Okay, so we've got in this, so we just look at this initial motion. So this is his V0x. He wants to have a minimum of 6.2 meters per second in the x direction to make that jump. Now, as he moves through the air, as I said, that x component of the velocity always stays the same. So really, we don't even need the V0 here. We could just call it just plain old Vx if we wanted, because it's really just a constant the whole time he's in the air. Okay, so notice I'm making these vectors pretty much all the same length. So as his path here, he's taking this overall path. Now when he gets to this building, okay, he will have an x component of his velocity that is still equal to 6.72, but his y component, although it starts at 0, it increases the longer he's in flight, depending on gravity. So if I know what the y component is, then I can figure out, combine it with the x component, and find his total impact velocity. So let's check it out. Let's go back to what we know. We know that the time he spends moving through the air was 0.92 seconds, and that was based on, remember, that y displacement, which was negative 4.2 meters. Okay. Oh, here we go. Okay, so he fell down, or was jumping down 4.2 meters. So we really have a couple of different options using this piece of information here, and then also that the acceleration in the y is negative 10 meters per second squared. So at this point, there's really two ways to find this final velocity over here. We can do it as a function of the time, okay, this 0.92 seconds. We know that gravity speeds him up at a rate of negative 10 meters per second each second. We could also do it as a function of displacement, negative 4.2 meters. So either or, both would work. Okay, so I'll actually show you both solutions here. So if I use my velocity as a function of time here, applied specifically in the y direction, Vy is V0y, the initial y velocity, plus Ay times t. So once again, that initial y velocity is 0, so I'll cross that out. And then I could do negative 10 meters per second squared times 0.92 seconds. And that would give me, let's see, negative 2 times 0.92 is going to be, right, 9.2. So, and actually it should be a negative, just to indicate that it is negative. The units of seconds cancels with one of those seconds over here, so that I end up with meters per second. So that would be one way to calculate the final y velocity. Okay, here is another way. So I'll put or. So Vy squared, this is now as a function of the displacement, is equal to V0y squared plus 2Ay, the acceleration of the y, times the change in the vertical displacement. So once again, we can simplify the initial y velocity 0, and then substituting in, it would be 2 times negative 10 meters per second squared times negative 4.2 meters. So let's do this math here. 4.2 times 10 is negative, well, the two negatives cancel, so that's 42. Times 2 is going to be 84, right? So there's 84 here. And the units would be meters squared per second squared. And the reason why it's important you recognize those units is because this is actually equal to the y component squared. So if I now do the square root of 84, let's see what I got. Sure enough, Vy is equal to it comes out to be 9.165. Now remember, when you take the square root of anything, you have a choice of having both a positive and a negative answer. This would be negative because it is in fact moving down. So it's a negative 9.2 meters per second. Okay, so two different ways to get the y component of the velocity. From here, we can now take a look at what is that x component and the y component together. What do they look like if I add them together? Well, you know, if you have two components in the x direction, two components that are perpendicular to each other. I'm just going to erase this so I have room here. We can add them together. Let's do a little sketch. So I've got moving in the x at 6.72 meters per second, moving in the y at negative 9.2 meters per second. The overall resultant velocity would be here. The angle of that velocity would be here. So now it's just a Pythagorean theorem and an inverse tan. Let's see, so 6.72 squared plus 9.2 squared, square rooted. So that would be 6.2 squared plus negative 9.2 squared. Excuse me for leaving off my units here, but I'm just running out of room. So then r comes out to be equal to, once I square root that, my calculator, that's going to be 11.4 meters per second. Okay, the angle here would then be, we would do, let's just erase this here so I have a little bit of room. So the angle then would be found by doing theta is equal to the inverse tan of the opposite over the adjacent, so negative 9.2, and in fact at this point we could probably just make that a positive 9.2, 6.72 here, and inverse tan of that, 9.2 divided by 6.72. Let's see, so theta then is equal to 54 degrees. And really, so just to be clear here, the reason why I kind of dropped off the negative in front of the 9.2 over here was simply because, you know, I've already accounted for it over here when I drew it in my picture. The negative indicates that it's a downward component. So when I'm looking at the triangle now, I'm just looking at these as kind of like the absolute values to represent those two sides. Okay, so that would be one way to find, say, the impact velocity or the final speed of an object after traveling, you know, through the air as a projectile. Okay, hopefully this helped. See you guys tomorrow.